thought I'd start on a philosophical note. So what I've worked on. All right.
Yours was? Oh, there.
There we go. Most of my career actually is on the psychophysics of the abstract percepts. Duration, rate, numerosity, probability, which we perceive as you go through the world. You have a sense of how far you went and how often things happen and how long things last and so on. And we share this with rats and mice and in all likelihood actually, well certainly for distance and direction, with insects, ants and bees. Philosophically it's interesting because these percepts have, there's no stimulus, there's no receptor for them and no qualia, right? When I think of red, I know what qualia means, but when I think of duration, all I think of is boredom. So they're percepts without sensations. And the second thing that's true about all of them, really, is that the percept doesn't happen until you've accumulated information in memory, and often over very long stretches of time. So, you know, how often does we have a sense of how frequently a 24-inch snowfall happens in New Brunswick. But it isn't every winter, right? I mean, so there's a stretched out over a long time in order to form this this percept. So in the present case, I'm talking about the perception of probability. And I want to start by making it very clear that I'm talking about descriptive probability. And I was assured by Brian that by Barry that, by somebody, Brian or Barry, yeah,
So
Brian,
if I'm wrong,
that everybody in this group would be clear about the distinction between descriptive probability and relative likelihood, but so let me go over it very quickly just to be sure. So descriptive probability is what I just described. You go through life and things happen and you have some sense of how different categories, how probable they are, you know. Driving from here to New York, how likely is it you'll see an accident on 95? And it's been known for a long time that in simple descriptive probability experiments, subjects are accurate over the full range of probability. And you'll see that that's true in our results as well. Now, some of you, or some people, are very startled to hear that because there's this whole literature on, you know, how people are systematically wrong. I should add, there are some situations in which people are systematically in error on descriptive probability, but I don't think anyone has any clear idea of why that is. For straightforward experiments of the kind I'll be describing, there's lots of, repeatedly been found that people are accurate over the full range. Contrast this with relative likelihood, the kind of experiment in which you're told that you're going to look at draws that come from one of two urns. And one of those urns has 50% green balls, and one of those urns has 80% green balls, and then you're seeing, you see 5 out of 6 green balls, and you're asked how likely is it that this comes from, or it's often phrased as how probable is it that that these draws come from the 80% urn. And there's a much greater, this is a much more interesting question, but not the question I'm going to talk about. And there's a much greater literature on it than subjects are systematically too conservative. They underestimate the relative likelihood that it came from the richer source. Okay, so here's the experiment that we ran. It's, I think, the simplest experiment I ever ran. It seemed so simple that I couldn't believe it hadn't already been done. And it was a postdoc, Monica Krishan, actually was running this. And I kept saying, look, Monica, I don't know the human literature. This experiment, somebody must have done this. It's your job to find it. We called Danny Kahneman. He didn't know anyone had ever done this. I emailed a few friends. They didn't know either. So then we wrote it up, sent it off to the second review, and of course the reviewers screamed bloody murder that other people had done this. Turned out there's only one, it had only been done once before, 40 years earlier, published in a relatively obscure journal. It was very gratifying, got identical results to the ones that I'm going to show you. So, in this experiment, subjects click on the box of rings whenever they want to see another ring, and a green or red ring emerges, and we ask them after every trial to indicate what they think the proportion of green rings is in this box. They do that by manipulating this slider here, which runs from 0 at no green to 100% green. And to sort of help them, but it was clear, all the subjects said they paid no attention, and when we ran ourselves we paid no attention too. But we had a box here that had 1,000 circles in it, and as you move the slider, the proportion of red to green in the box changed. We thought maybe they wouldn't have a sense of what the slider meant, but people had a very good sense of what it meant. As soon as they, after a moment or so, the circle evaporated, and then they would click to get another circle. And subjects ran 10 sessions of 1,000 trials each. This is psychophysics. It's like almost all psychophysical tests. It's very repetitive, very boring, right? But it's fast. It only took the average subject about 25 minutes to run off 1,000 draws from the urn. We told them at the beginning that occasionally we'd silently swap boxes on them so that the proportion might change, but we said nothing about by how much it might change nor how often it might change. I'm sorry, they drew things by clicking on the next, not by clicking on the box. And we asked them that when you think the proportion has changed, please click on the box has changed button. And the first 5 subjects that we ran all spontaneously remarked at the end of the first session to Monica that, you know, sometimes I clicked, I said it had changed, and then when I saw some more circles I thought, no, it hasn't changed. And I said, oh, that's very interesting and very important. So we added a button for the last 5 subjects, and that's the I take that back button. So if you had second thoughts, you could click on the I take that back button. Everybody clear about the experiment?
Well, did you ever change?
Yeah, oh, sorry. So the true P did change in steps. We'll come to a second version where it changes smoothly. The steps were largish, but completely unpredictable. They were scheduled by coin flip. And they were infrequent. So the expected number of flips without a change was 200. But it was geometric, so there were, in fact, cases, remember, there are 10,000 trials for each subject, so there were cases in which there were only 1 or 2 trials between changes, which of course were totally undetectable. So that's the experiment. And everybody clear about that? So this is what the results look like. And Robinson's results looked exactly like this. And he had quite a different system. His was pre-computer back in the early 60s. His subjects were looking at 2 flashing lights. They had no control over how often they flashed, and one was red and one was green. They were just supposed to say what the probability of a red flash was. And they indicated that they had a little lever that they were holding, which was very easy to move, and they had a dial. When they moved the lever, the dial went from 0 to 1, and so the sort of details of how he did it and his protocol were different. But when he looked at what the subjects indicated, you could substitute his records for ours and vice versa. They look exactly the same. So the true P is what you see here in the dashed line, right? And here's what the subject thinks the P is. And as you can see, the subject's doing a reasonable job of tracking the true P. But what you see is that the subject was not moving the slider on every trial. The subjects would leave the slider in a given setting for long stretches of time. So they moved it intermittently, and when they were moving a lever, exactly the same thing was true. The other thing you see is that they moved it in big steps. So sometimes the subjects would move the slider from basically like 0.96 to 0.02 in a single trial, home. But they also made lots of little movements. Here you see a bunch of little movements. And as you can see in this record, I said already, and you see it in actual data from an individual subject in a single session. This is only 1 out of the 10 sessions for that subject. But you can see they're pretty accurate. I mean, they're not foolproof by any means, but by and large, they're pretty good. And moreover, how accurate they are is independent of what the p-value is. They're just as accurate at 0.05 as they are at 0.5. Now, I'm not sure in this audience. If you think a little while, you think, well, what's your measure of accuracy? I see. Jacob is grinning here, right? This is probability. Mean square error isn't really where it's at, right? And we did it mean square error because we figured half the readership would insist on mean square error. But a much more valid measure is the Kullback-Leibler divergence. I don't know whether it's worth going into that, but it's an information theoretic measure. It measures, suppose you think you're drawing from a distribution that's 0.5 and you're actually drawing from a distribution that's 0.8. Or you're actually drawing from the distribution that's 0.9. Well, it's intuitively obvious that when you're drawing from a distribution, when the error is big, you're getting more information every time you draw, on average, about your error, right? And in fact, the Kullback-Leibler divergence measures the amount of information that you're getting about your error on each draw, right? So you can convert it into how many draws would you have to make in order to know that you were in error, right, at the 0.05 level. And the average across our subjects was 100 draws. So that's how accurate they were. That is, they were on the average trial, it would have taken the discrepancy, and also not between them and the true probability, because the true probability is known only to God and MATLAB, right? But the probability of an ideal Bayesian observer, right? So the question was, how far away are they from the probability of an ideal Bayesian observer on the average trial? And the answer is their error would have taken them 100 draws to discover. So that gives you a feel for the accuracy. And I told you people are accurate. Yeah, Jacob.
So, I'm sorry, an ideal observer with what assumptions?
Well, so an ideal observer that's estimating the prior probabilities from his or her own experience, right? So there are two things in play here, the prior odds and the Bayes factor, right? And we told the subjects nothing about the probability of a change, right? And it was clear from the data that subjects thought the probability was higher than it in fact was, and that in the course of the experiment they learned, they corrected themselves, and this had the appropriate effect on how often they detected a change.
So their prior on stuff like that was asymptotically correct.
And their prior was headed toward asymptotically correct.
But when you're calculating the ideal observer, it's going all the way back to the beginning of the experiment when they might not have had the right prior.
Yes, the subject clearly had the wrong prior. Our model and the ideal observer converges on the correct prior much more rapidly than the subjects did. Our model, which is close. It isn't an ideal, our model of what subjects are actually doing isn't an ideal observer model, but it's not far off it. And it converges on the correct probability of change much more rapidly than the subjects do. But the subjects are, in fact, converging on it, and all of them are. I don't know, do you want to go into the Bayesian? I don't know how many Bayes fans we have here, but it's a lovely illustration of the distinction between the prior odds and the Bayes factor. Because this kind of change detection, I guess I'll say it's clear from expression that that isn't immediately obvious, so I'll say a little bit about that. So, if you know that things change, then whether you know it or not, somewhere in your brain you have a guess as to how often they change, right? And it was clear our subjects did. Oh, by the way, we asked our subjects what they thought the proportion was before they saw a single circle. And they were all close to 0.5. Right? So maybe that's just convention, or maybe they actually have a prior on the p-value. But the more interesting thing, which is what Jacob's question raises, is what's their prior on how often it changes?
Yeah.
Which is a separate issue, right? Now, if you think it changes once every 100 trials, and you've seen 1,000 trials, I wouldn't even bother to look at the data. I'd just say, well, there's been a change. Because just knowing the length of the sequence you was observed and having an estimate of the change, probability, the odds are overwhelming. If it changes once every 100 trials and you've seen 1,000 trials, the odds are overwhelming that there's been a change in there. So even if the data don't look very much like there was a change, it would be crazy to bet against the change. So the length of the data sequence determines the prior odds in a full Bayesian calculation, which is the prior odds times the Bayes factor. And the Bayes factor depends upon the actual distribution of the green and red circles within the sequence. But the prior odds is given before you looked at the sequence. So it really illustrates what prior odds mean.
Follow up, have you
Yeah.
manipulated what the prior odds would be?
We haven't. Well,
Seems like an obvious experiment.
when you get to smooth changes, we could raise the question again when we come to the smooth changes part of it. But when it comes to smooth changes, then it's, particularly for some of the subjects that we're looking at sinusoidal changes, then it's changing by a little tiny bit on every trial. Or almost, actually.
Well, yeah, okay. I mean,
Okay? But, Brian, you're, no, okay.
I'm wondering if did you keep track, or did you compare? So everything you're comparing here is the estimated p versus the true p.
No, versus the ideal observer p.
Okay, so did you compare to if you just take the empirical frequency for the past so many trials, was that, was their estimate in any way related?
Well, what the
correlated with
ideal
that?
observer is doing is very close to that.
Yeah, I was wondering how close to that
The
it
ideal observer is telling you what a particularly intelligent observer would conclude from what is actually seen.
What is
Yes.
the ideal observer's model?
I'm sorry?
I guess I have not quite grasped what the ideal observer model is.
Well, part of the nice thing about this is when Robinson ran it, there was no ideal observer model, but then Mackay and Adams published a quite general ideal observer model that applies to a number of distributions, but particularly to the Bernoulli. In the ideal observer, the ideal observer is carrying forward simultaneously the probability that there was a change 11 trials back, the probability that there was a change 10 trials back, 9 trials back, 8 trials back, and evaluating what the current probability is, taking into account both the probability that there was a change that far back and so if you think that there was a probability 10 trials back, right, and then you look then you look only at the data for the last 10 trials, right? And that gives you a purely empirical P, and then you weight that by the probability that there was a change 10 trials back. Follow that?
No, I guess what's in my head is that I would imagine there are infinitely many different models you could have.
Not
So
for
when you say,
Bernoulli. Sorry. Well, there are it could have changed.
I mean, there are different ways of modeling it. You said somebody published a model, but somebody else could have published a different model. So
Well-
when you say the ideal observer, I guess that's what's leading me a little astray.
Well, I'm not a professional statistician, and so I'm likely to get in over my head here fairly rapidly, but I don't think there's much disagreement in the field that this is essentially an ideal observer model. That this takes into account all the, Jacob can comment on this.
I mean, there are always an infinite number of ideal observers.
Yes.
The field doesn't like to recognize that, but there are.
Yeah.
But they're all very close to each other.
Yes, right.
So yours making a couple of assumptions like, like the probability can only change on each trial. It can't
Right.
change 10 times between two draws. for example.
Right, right.
But once you wipe out a lot of sort of pathological
Yeah,
model sets like that, then
Right.
you're left with a pretty narrow range. So,
yeah,
I mean, I think it's fair to say that there's close to an ideal,
yes.
unique
yes.
ideal
Yeah.
observer, but it's not perfectly unique.
Yeah.
I mean, like what I was asking before.
Nothing I'm gonna say hinges on whether this
Yeah.
is the ideal observer, but yeah.
So you're talking about the prior that the subject might have for the probability of a change.
Right.
But there's also the question of what assumptions they're making about the prior over the true P.
Yes, yes, indeed.
And there again,
And we
there's like-
modeled that, yeah.
Yeah, I mean, there are standard answers for that, but you could,
Yeah.
like kind of say, you could
Yeah.
quibble with those standard answers
Yeah.
too.
Yeah, yeah, well, of course, that's a purely empirical question now. I mean, the subject could have a crazy prior over P, but in fact, if you model them with a Jeffreys prior, it looks pretty good. So the Jeffreys prior is an uninformative prior. It's now we're not talking about the prior on the probability of a change, but what's the prior on
Yeah.
the P itself? Everybody clear about this distinction? Right. And every time you think there's a change, of course, that prior comes into play again. You start updating that prior anew. And the Jeffreys prior is beta 0.5.5, so it's a highly uninformative prior, and it has a lovely property in that it's invariant under change of parameter, but I don't think we I'll say a little bit about that. What if we parameterize in terms of the odds? I mean, if there were a bookie in the room, right, he'd say, what are you doing about P? P is not the right way to think about probability. You should think about the odds, right? Well, Jeffreys was the first to raise this question, and it turns out when you do a Bayesian calculation, for most priors that you might choose, in fact, for all priors except the Jeffreys prior, if you think that odds is the appropriate way to conceptualize the problem, then when you have very little data, you will get a different answer than you'll get a different estimate of what the p-value is than you would if you thought P was the right way to think about a Bernoulli process. Sort of a mind-bending fact. But the Jeffreys prior has the unique property that that's not true. That if you change from thinking about it in terms of P to thinking about it in terms of the odds, and make the appropriate change in the prior, then you get the same answer whichever way you calculate. I never would have thought of that in a million years. That's the difference between a genuine mathematical and me. So these second thoughts. I mean, I think these second thoughts are very important. So you might ask, how late do they occur? Well, here's the cumulative distribution of second thoughts. Some of them occur hundreds of trials afterwards. Sometimes the subject hasn't changed, hasn't said there's been a change for 250 trials, and they say, you know, I don't think there was a change back there. But most of them, as you would sort of expect, 80% of them occur within the first 20 trials after you said there was
Randy,
yeah.
you want to make it clear that these are the data for a subject saying, oops, I was wrong.
Yeah,
Yeah.
second thoughts.
And-
Yeah.
Yeah, but what you didn't.
Okay, well, it's right there on the.
So then they
Yeah.
change, they go back.
Huh? Yeah, they'd say, they click the thing that says, I take that back, right? So this is how many trials between when they said, I think there was a change, and they said, I take that back, right? And so you can have second thoughts way down the road. Now, let's return to this step thing. I know what you're thinking, and
Randy,
you're
can I
wrong.
just ask?
Huh? Yeah, sure.
That graph, were they correct in saying there wasn't a change? So this is
You
a
know,
more accurate child?
we looked at that, but I don't remember. I'm embarrassed to say, I gotta go. At one point, I spent years analyzing the data. At one point, I looked at that, but we didn't
Sure.
publish it, and I've forgotten what the answer was. So I know what you're thinking about these steps. You think, the subjects are, they're lazy. Well, let me say a little bit about why the lack of steps are surprising. There are a lot of models out there. They're both Bayesian models and much more commonly associative models that use delta rule updating, where you, on each trial, you look at the discrepancy between what you, quote, expected and what you observed, and then you move in the direction of what you observed by some percentage that's determined by a prime, usually called alpha, right? So the vast majority of the models look like that. But intuitively you think, well, the subject's updating every trial, right? Now, with the Bernoulli process, what you see is always 0 or 1. Right? So it's always a long way, or not always, but more often than not, if you're somewhere in the middle in what you think the probability is, then on every trial you're seeing something that's a long way away from what you think. So if you apply delta rule updating to this, you should be jerking that estimate around. And how violently you should be jerking it around depends upon alpha, how slowly or rapidly you're moving. And so the fact that subjects aren't moving on most trials was already against practically every theory, not practically, it was against every theory that was out there. But even some of my co-authors, most notably Peter Latham, it must have taken me 20 emails and several Skype conversations to make him see that the data I'm showing you now showed that what he thought was true could possibly be true. That is, instinctively you think, well, subjects, they don't want to, it's so much work to move that slider. And so they don't move the slider unless they really think there's been some sizable movement away from what they think. So there are 10 versions of that, but they all boil down to the subjects are lazy or disinclined to make small moves, right? And they all boil down to the statement that subjects won't make small moves. But in fact, small moves are the most frequent moves that subjects make. This is a plot of the step width logarithmically. How long they left the slider there before they moved. You see that sometimes it was, and the record here was almost 350 trials, right, without moving the slider. And when they did move, what was the absolute, how big was the move, okay? And what I want to call your attention to is the marginal distribution on the size of the moves. And the mode of the marginal distribution are the two bins on either side of 0. Right? the smallest possible moves, right? So, oh, the reviewers. So we dared them to. We showed simulations, we did the algebra, we said, look, there's got to be a hole in this distribution, and there isn't. And any model that says you're reluctant to move is going to produce a hole in the middle of this distribution, and there is no hole. Yeah.
Without
Yeah.
attributing laziness to
Yeah.
it, couldn't there still be a gap between the reporting and the perceiving?
Sure.
And that the reporting is just conservative and delayed?
As I
relative-
said, any version you want to put out there is going to produce the whole. It doesn't matter how you phrase it. You don't have to insult the subjects. You can just say they're conservative. Right? In fact,
The whole of,
it's going to. So, if you think it's 0.1, if you had thought, if you got the slider set at 0.1, and now you think it's 0.9, presumably everybody's going to move, right? So what does conservative mean other than that, well, I'm not going to make movements if I'm only out by a little bit? Isn't that, I don't know what you mean by conservative, but.
I just mean I'm only going to wait, I'm going to wait a while before I commit to it moving it just a little bit. That I'm going to let more evidence accumulate before I make a tiny move.
Oh. I'm not, that's exactly right.
Oh,
Oh,
okay.
that's exactly what we think is going on.
Okay.
We call that, if it ain't broke, don't fix it,
Right,
principle.
yeah, okay.
Right? And I'm going to suggest at the end that it's a very general principle of perception. That exactly as you said, hey, I haven't seen any serious evidence that I'm wrong, why should I change my opinion? Yes,
Well, I
Sarah?
was just gonna say, you can definitely, or I would imagine you can take that into account, that may vary by participant, where some are more or less conservative.
Oh, yeah.
They're gonna have their own internal
For sure.
criteria for that, it's gonna be consistent throughout trials.
For sure, and there are exactly those kinds of individual differences,
Yeah.
right? Some subjects move much more often than others. And this is just throwing them all together into one
Exactly.
scatter
So
plot.
the slider moved by clicks?
By a mouse.
No, but I mean,
Oh.
you were talking about bins, bins on either side of the zero.
Oh, well, we did, in order to make this kind of histogram, you have to bin, and we binned by 0.01.
But the slider itself did not move continuously or moved.
It would move by pixels, obviously, and 1 pixel was less than, that is, the minimum movement on a monitor is 1 pixel.
But when you moved it, you didn't have a sense of it going by clicks or something? You
No,
just-
it was perfectly smooth. You know, this was a Macintosh with a pretty good quality screen. The thing appears to move perfectly smoothly, but of course, in fact, it's moving 1 pixel at a time, and I don't remember how many pixels made 0.01, but it didn't seem likely that subjects actually had a representation more accurate than 0.01. You're rounding, Jacob. Okay. So, why the steps? This is your conservative model, right? We assume a 2-stage model. One stage does a simple computation to decide whether the current estimate is doing okay, right? And if it's because it's very, again, it uses the Kullback-Leibler divergence, which sounds pretty fancy, but computationally it's very simple. And it has lovely properties. So there's a very simple computation that says whether you got a problem or not. And if you don't have a problem, on to the next circle, right? If you do have a problem, then of course you got to figure out where the problem come from, right? And there are three possibilities if you think about it. Well, Jacob thinks about it, there might be more than 3, but there's 3 obvious ones, right? We never considered the multiple changes between one trial. Seemed like that would come out in the wash. So the first possibility, which is almost certainly both in the model and I think in the behaviors, the subject, I forgot to say, but the subjects detect that you saw in the plot, the first thing, the subjects detect the changes rapidly. And they make these big adjustments to big changes. So because they detect the changes rapidly, they don't have much data. So they're looking back and say, oh, yeah, how in circles, I think it's changed. Well, the only thing, it would crazy, the subjects aren't stupid. If you think it's changed, you don't include the data from before when you think it changed, right? And if you're good at detecting changes and the steps are pretty big, then when you've detected the change, you don't have much data to estimate what the new p-value is. Quite often in the model and so on, you only have 4 or 5 observations, which is a very small sample set when it comes to estimating a p-value. So very often the reason you're wrong is small sample error, right? Your current estimate was based on a very small sample, and now that you've seen more data, you have a better sample, and you see that, not surprisingly, your first estimate was a bit off, and so you change, usually by not very much. That's why you get so many of these small ones, right? So that's the first explanation for what the problem is, why your current model hasn't been doing as good a job as you would like of anticipating what you're seeing. But the other obvious one is that there's been another change. But then there's a third, less obvious one, although the second thought was a big flag that no, the third explanation is that that was a garden path that caused you to make the last decision. That last decision was an error, and you will get a better model by going back, wiping out that last decision, and looking at all the data. Notice the implication here, that you actually have the whole sequence in memory. Yeah, right. You can imagine how the reviewers loved that one. Looking at all the data going back to the previous change, whatever that was. Right? And it's even possible that nothing in the model prevented this, and in fact the model at least could, very rarely, but there were occasions when the model would even decide that the previous one was, it could go back and say, no change there, and no change there at all. It never went more than 2 change points back. So those are the 3 possibilities, and we used Bayesian model selection to decide among them. And I'm not, people want, I'm happy to go through it. It's very straightforward when it comes to Bernoulli stuff. And that's where the prior odds came in and so on. So this is a full Bayesian model of the subjects, right? That they're estimating the p-values and they're estimating the probability of the change. And if you think about it for a moment, you say, whoa, these are going to interact. And of course they do. I mean, because as I explained before, if you think there's a high probability of change, then you've seen 50 observations and you think, well, they wouldn't waste my time in this experiment unless they were making lots of changes. And you think, boy, I'll bet there's been change, so that's the prior odds. And so you don't take much evidence within the actual sequence in order to decide that there's a change. So if you're really taking the prior odds into account in this way, which you should be doing if you're a really shrewd observer, then you will make more change detections in the first 2,000 trials than you will in the last 2,000 trials. And that's just what subjects did. Yeah.
You just said that you go back and have all this stuff, right?
Yeah,
The alternative, there's a compression model.
right. Well, we can return to compression, but if you throw away the data, then you can no longer compute the Bayes factor.
All right. That's an interest,
All right.
Well, the frequency is a sufficient statistic for the Bayes factor. So you don't need the actual data, you just need high frequency.
No, you need the likelihood function over the previous trials. Because you have to estimate where the change occurred. And the frequency is a sufficient statistic only if you're given the
Sample,
relative. Yeah.
No, I don't mean it's one frequency, you have to remember the function as you go back in time. How
well,
many
yeah,
there were
right.
as you go back, but you don't have to remember.
I think that that's invertible. I think you, from that you can get back to the sequence. You're saying you remember the likelihood
Yeah,
function at each
yeah,
point.
right.
So what you
Yeah.
actually did was, every time you made a change, you drew the new probability from the same probability distribution.
No, no, no. No, I mean the program, the underlying program. We had an algorithm, and I won't bother to, we wanted to make most of the changes pretty big. So we had an algorithm that forced changes to be pretty big. But they varied a lot in magnitude, but there were no changes of 0.01 or even 0.03 or 4. But when it flipped a new thing, it drew a probability at random. It would reject them if the change was too small and keep drawing a new probability.
And that random means uniform from zero.
Yes, from a uniform distribution.
But
of
your
the-
subjects did not know that this.
They did not know
was
this.
rules.
That's right. You can see that, right?
But your ideal observer model knows.
The ideal observer doesn't know that either. You can, I mean, you can see right, right there, right? I mean, the true probability went from 0.95 down to,
So what is the ideal observer model?
well, that's what I.
It doesn't know, the ideal observer model does not follow the same assumptions as what you were doing.
Well, the ideal observer is updating his estimate, her estimate of P every trot. So, yeah, they're not behaving, the ideal observer is not behaving like our model.
The ideal observer is estimating a new probability that is if it had been the probability all along.
Nope, that's what I explained before, I'll go through that again. So the ideal observer is computing two probabilities. It's computing the probability that there was a change X trials ago for every value of X. Okay. And it's computing the probability that you would estimate if there had in fact been a change X trials ago. Okay?
And there could have
And-
been other kinds of ideal observers. This was your ideal observer. I got you.
Oh, yeah.
Okay.
And.
Sorry.
Yeah, yeah. So that was that was our ideal observer. So, okay, so let's see. Did I skip this? Yeah, okay, so, as I say, unless you want me to, I'm not going to spend a lot of time on, but it's Bayesian model selection, right, between those three possible explanations. And if you conclude that there's been another change, then you're keeping a record of the changes. This will be important later on. On this story, the changes themselves are every bit as much events as are the circles. Because you perceive that there wasn't a change, and that's an event, and you've calculated the probability of that event too. And we'll see, I think that leads into interesting territory, and we'll get there at the end. So why the second thoughts? Well, I think maybe at this point it's obvious. If you're talking functionally, ideal observers should have second thoughts on this story. And that's because the future is informative about the past. One of my favorite novels is The Good Soldier, Ford Malisor's The Good Soldier. I mean, there are many novels that do this, but The Good Soldier is sort of the whole thing where it's a story of this guy's view of his own marriage, right? And you're reading along, it looks like he's got a very plausible view, it looks like that's the truth, and then you start learning other things, and after a while, you realize, and he slowly realizes that a completely different narrative of what was going on is appropriate here. And as an undergraduate, I found that fascinating. But now I see there's a deeper truth. Even when we step outside the fraught ground of marriages, the future is in fact informative about the past. Because the future tells you, for example, these garden paths, right? And now, the nice thing about this is that there's a rigorous sense that defines what garden paths are. And that's of some interest in that the minimum description length comes in here. That is, what this Bayesian model selection is really doing is selecting the model that would take up the least amount of room in memory. It's the most efficient coding of the past. And these every time you add a change point, you make a more complex encoding. And the nice thing about Bayesian model selection is it penalizes unnecessary complexity. All right, so it's enforcing an efficient coding of the past and using that to anticipate the future, which is, yeah.
But I thought you said earlier that they were keeping all of this data in case they need to go back and reevaluate.
Absolutely,
So-
but now we're getting to, this is what actually interests me the most. As long as the probability isn't 0.5, right? For any Bernoulli sequence where the probability is not 0.5, I can encode that sequence in fewer bits than the number of bits that I've seen, right? But to do that, I have to estimate the p-value. And the more accurate the p-value is, this is Shannon's coding theorem that we're dealing with here, right? That you can, if you have an accurate, that in order to construct the most lossless code, okay, we're not talking about savings because we're using the mean. We're talking about you can recover the data entirely, but in a 1,000-bit sequence you use only, say, 800 bits. Right? So that's and it does two things. This is what emerged from Riesonen's minimum description length, which Jacob put me onto, which has become an obsession of mine recently. But adopting this perspective does two things. It allows you to make more efficient use of your memory, and there's a theorem that the stochastic model that most efficiently encodes the past is also the best predictor of the future. So it's a double whammy. It does two very good things for you. So on this story, you're recoding the data. Now in psychology, there's a tremendous literature showing that people have, and animals, rats, and so on, routinely recode the data. In fact, it looks like they do a lot of it during sleep. As far as I know, this is the only story that explains why this might be a sensible thing to do. Up until now, it's just been one of those crazy things that brains do. Right? But maybe it's not so crazy. Okay, so then Matthew Ricci, who was a Penn undergraduate, came along and did a follow-up experiment here. So we made step changes, right? And maybe that's why our subjects treated this as a stepwise change problem. And also, years ago, Bill Estes did an experiment in which, very similar to this, in which the probability changed sinusoidally. And he had subjects look at this for a while, and then he had them draw what they thought was going to happen. Or he had two things. It went flat, and subjects tended to sort of show a damped oscillation after the probability went flat. And also, if you had them draw it, they do wavy ones. So he concluded, he had a delta updating model which wouldn't detect this higher level structure. He concluded that his model wasn't adequate. So we wondered what would happen, and actually the editor wanted to know what would happen too. But he let us publish the first one without doing this. But then we got around to saying, well, what happens if the probabilities change smoothly? And we can do this in two ways. We can do this aperiodically. That is, we can take those step changes that you saw before and just apply a filter to them so that it smooths out all the cliffs. And so now all the changes are smooth, and the underlying p-value doesn't change by more than about 0.01 on any one trot. But the other obvious thing is what Estes did, which is how about if there's structure to this change, and what if it's periodic? So we had it change sinusoidally with a period of 200 trots. And Robinson, the guy who did it with the lever back in the 60s, said at his last paragraph that he ran a pilot experiment with continuous changes and he still saw step changes, and so do we. As you can see, now the dashed line is the subject, which is annoying, but this is the way Matt plotted it, so I haven't gone back and gotten the. If I had more time, I'm going to replot this with the solid line as the subject and the dashed line is the true p. But anyway, as you can see, the subject is making sense. And the cool thing is, down here, this subject, these are different subjects. This is an aperiodic subject. This is a sinusoidal subject. This subject, all the subjects in the sinusoidal condition said at the end, oh, it varied. They all knew it varied periodically. They didn't actually show, this subject is kind of trying to guess how it might proceed, but and a subtler analysis of what they did showed that they differed from these subjects quite strikingly. But as far as I was concerned, they all said it varied periodically. I mean, they all knew that it varied periodically. But you can see that even though they were tracking, they're tracking it in steps. What they're doing is using their knowledge of the period, so when they get to this point, they make big steps. And then up here, they make small steps. But they're tracking it in steps. No, we've never seen a subject. So none of Robinson's subjects tracked continuously. None of our first 10 subjects tracked continuously. Michael Woodford, a behavioral economist at Columbia and a postdoc of his, used our code to run a replication. And I'm not sure, I think they had 20 subjects. And they paid their subjects for accuracy. We didn't, because they're economists. You can't publish in an economics journal if you don't pay your subjects for performance. But psychologists have much less faith in the market than economists. So the bottom line is that now about 50 subjects have been run, and there's never yet been a subject that tracked track probabilities smoothly on every trap.
So on this bottom one, so you can see
Yeah.
that the you said the black line is the true.
That's the true probability,
right?
yeah.
So that means that the subject was still trying to mimic periodic.
Oh yeah.
Even when it wasn't, right?
Yeah, although when we ran a test for periodicity, it sure looks like periodicity, but when we ran various tests for periodicity, even in this subject, they were only very marginally significant, and in other subjects you didn't see nearly as much of this. So one of the other subjects pretty much just flattened out, boom, after a little bit of this kind of back and forth, and then boom, just flat. Which is what many of the aperiodic subjects did when it went flat as well. In fact, look at you. Well, here you see.
So this wasn't a typical picture.
They're fairly pronounced. This subject was tracking exceptionally well. Everybody was tracking more or less, but most of them weren't tracking as well as this subject did. But all of them were tracking in obvious ways, and all of them said they noticed the periodic changes.
What were they told in this one?
They were told that exactly the same thing as in the previous one.
Which was what exactly?
That it
May
might
occur.
change. We didn't ask them to
Changes
click.
may occur.
Changes may occur, yes, exactly. We didn't ask them to click when they thought they'd occurred because it didn't make sense in this one. But that was an omission, that is, we say changes may occur. End of story. Up to you to figure out how they happen.
I feel, can I
Yeah?
ask you?
Yeah.
I feel there's something very counterintuitive about this, maybe, so maybe I'm not understanding the experiment. I mean, how is it possible to track it so well somehow? I mean,
Well,
my
keep-
impulse
look
my
at
impulse
how
would
many
be to
trials
just
we're talking about
keep it
here.
steady maybe for 200, 300 trials. And then, so I would expect a flat line, say from
Well,
from the beginning to the next
The
time
next
it's
slide
0.5.
may help, I hope if it's visible. Yeah, okay. This is actually a simulation, but it shows you, this is actually more rapid change than our subjects were experiencing. And this is sinusoidal change. This is MATLAB, okay? This sequence was generated by MATLAB, drawing from a Bernoulli distribution whose p-value was changing sinusoidally with a period of 60, I think. Okay? And up here you see the green circles. Can you see them? Can everyone see them? And down here you see the red. Okay, so, and you can see the changes. I mean, and experiencing them sequentially is just as striking as seeing them spread out in space here, right? I mean, for a while you're seeing not very many greens and quite a lot of reds, and then, ooh, I'm seeing quite a lot of greens, not very many reds, ooh, and now I'm seeing quite a lot of reds again, and so on. This is truly perception, and subjects are not counting or anything, they're just going along here, clicking, and I'm just trying to give you a feel for the kind of experience.
I mean, that's very visible on the...
Yeah,
On the
so
one
here's
below.
the aperiodic, right? But here's the periodic. And here's, I said earlier that the changes that are themselves events. And now we get to what I was looking forward to. Because these are Bernoulli events too, the triangles, right? Well, of course, they're on a completely different time scale. But this is a model of what the brain does when confronted with Bernoulli events.
What are the triangles?
In order for it not to make a model of the triangles just like this, we would have to put in something that say, oh no, don't, don't model those events, only model these events.
What are the triangles?
The triangles are, oh, sorry. Yes, thank you. The triangles are when we ran our change detection model on these data, and that's where it thought the change events occurred. Okay? You'll see that it's behind, it's out of phase, of course, right? That is, it detects the upswings and the downswings after they have occurred, which isn't surprising. Okay? But what I want to emphasize, what you're looking at here are three events. These are not Bernoulli events because they're changes in a periodic structure. So these cannot be well modeled by Bernoulli. But more generally, we have two models. We have a Gaussian and a Bernoulli. And a Gaussian will model these very nicely. And where you can predict how many trials it'll be to the next change if you have an estimate of when this change occurred. Right? But down here, we're looking at aperiodic. And this is an aperiodic sequence. And these are where our model detects up ticks and down ticks, right? And these are random. These are Bernoulli changes. Bernoulli changes in a Bernoulli process, right? But what this says is that this model will automatically construct a hierarchical representation of this experience. You would have to intervene to prevent it from constructing a hierarchical representation of these experiences. Then, the fact that, so there's a lot of thinking about where hierarchical structure emerges in memory, and on this kind of efficient coding story and change detection story, it's going to just come. You don't have to do anything to get hierarchical structure. The question is, how would you block it, not how would you get it? see, this is the lower order stream of events, and this is the higher level stream of events. But the point is that exactly the same modeling for, well, in this case, exactly the same modeling is appropriate for the higher level sequence which supervenes on these lower level events. Here.
There you go. Uh-oh.
Interesting.
Did they make you start over?
I don't know why.
Oh, there you are.
Don't tap on the screen, I guess.
Said no time left, by the way.
I'm always inclined to try and make a lot out of a little. I said that I gave this talk at Brown about what real learning looked like, and the slogan was that real animals learn a great deal from very little, and convolution neural networks learn very little from a great deal. So I belong to the real learning thing. I always try to learn a lot from very little, right? So here's what I think we can learn from this. And of course, this is generalizing way beyond the data. That's the whole point. And, so I think that this, if it ain't broke, don't fix it, is a very general principle in perception. It's a huge labor saver, right? If we got a pretty good model and the world looks like it's conforming to the model, don't trouble your little old head about what else might be true. Just keep plowing along. And so on this story, what we think we're seeing and anticipating of the world is overwhelmingly driven by memory. It's driven by the model that we have in memory, which is making predictions, and generally we're saying, yeah, just what I thought. And then we don't think further. And we only think further when what we see fails persistently. Not, the world has to be persistently annoying in order for us to start thinking about it. And it's annoying by not turning out as we anticipate. And therefore second thoughts are common, and they should be, because the future is informative about the past, and what we're, that isn't mine, is it? And so what we're trying to do is build this good predictive model, which will also save us memory, and that's why Bayesian inference is ubiquitous, or the minimum description length, which is another way of penalizing for complexity. A principled way of penalizing for complexity. There are many sort of ad hoc ways of penalizing for complexity, but using priors on model selection or using minimum description length is a deeply principled way of penalizing for complexity. And what that does is implement this age-old intuition that simple models are better than complicated models as long as they're not too simple, which is, it was Einstein's way of phrasing Occam's razor, right? That we want our models to be as simple as possible, but not too simple. And the question is, how do we achieve that? And current answers are, there was no glimpse of this when I was 50 years ago, is that, well, Bayesian inference or minimum description length is a mathematical realization of Occam's intuitions. So I thank my collaborators, Monica, who who did the code that ran the experiment and ran it, and he who helped her, Peter Latham wrote an ideal observer model of his own, which is the one we actually use, but it basically mimics the Adams and Mackay model perfectly. I mean, as Jacob said, you could make slight differences in the models, but they generally make very similar predictions. And then Matthew Ricci, who ran the smooth learning thing.
So one thing I wondered about, which I think has to be somewhere in what you said, but I don't think I got it, was, so, about the second thoughts. So,
Yeah.
I mean, part of the reason why you have second thoughts is because, because Bayesian inference is sort of non-monotonic in the data, right?
Yeah.
So when you get more data, you can change your mind.
Yeah.
But you can change, so, if you were simply going by the Bayes factor,
Yeah.
then every time you change your mind,
Mhm.
the next data that you get has a pretty high likelihood of changing your mind back,
Yes.
right? And clearly your subjects aren't doing that.
No, they aren't, and that's, you're right, and that's where the ink broke. So remember, there's this other computation which I didn't describe, and given your very penetrating question, I'll now describe it. So, what the subject does is look at the Kullback-Leibler divergence between the raw, so it thinks that there was a change seven trials back, right? And suppose that it's seen 5 green circles and 2 red circles, okay, in those 7 trials. And so I should have chosen better numbers to calculate in my head what the p-value is, but anyway, so we get a raw, straightforward p-value from that, right? For the green circles, 5/7. And suppose the subject estimated when he detected it, he estimated after 4, right? And he thought the p-value was 0.95, right? So he's flying on the assumption that he's looking at a 0.95 process, but he's seen 5 out of 7. How upset should he be, right? So you calculate the Kullback-Leibler divergence between 0.95 and whatever 5/7 is, right? And you multiply that times 7, right? So it's n, the number of observations times the seeming discrepancy. And there's where Peter Latham earned star billing in this. So it turns out that statistic has a fixed distribution that's independent of n. That statistic, n times the Kullback-Leibler divergence, is distributed gamma 0.51, period, regardless of n. This blew my mind. I discovered this more or less just messing around in MATLAB. I was running simulations in MATLAB, and it looked like I could always fit these things with a gamma distribution, and always with the same gamma distribution. Those of you who do frequentist statistics will realize that a statistic that doesn't depend on the n is almost unheard of, right? Now, we used to have tables in which you looked up your n and so on. So to have a statistic whose distribution doesn't depend on the number of observations is really weird. So I emailed Peter and I said, Peter, messing around in MATLAB, this looks like this kid. Looks like this might be true. I thought it was gamma 0.5, I think. And Peter is 10 times the mathematician that I am. And so a week goes by and an email comes back and he says, I get 0.51, followed by a proof. He proved that this is in fact distributed gamma 0.51. And that's what I mean by a really simple computation, right? And it's that prevents this jitter at the boundaries that you, and if you take that out, you do get the kind of jitter that you're concerned about.
If you take it out.
If you take out this, so this calculation is never going to say that there's been another change after 2 observations, right? It's like a damper if you think about it mechanically, right? It's so, well, never. I mean, obviously, if the probability of 1, it'll change. But basically, this remember, it's a 2-stage model, right? Every time you get a new data, you update this calculation, but updating it is trivial because the distribution is fixed, and the Kullback-Leibler, it's a. I could write it out for you, but trust me, it's really simple. So it's a trivial updating calculation. And all it does is tell you whether you've got a problem or not. It doesn't tell you what generated the problem, and so on. But it functions as a buffer to prevent the jitter. And so you never end up going into the Bayesian calculation unless there's some serious reason to think you do have a problem.
So like if that test fails, then you do.
Yeah, right. So if that test passes, so our model, which does, in all modesty, quite a good job, only has 2 free parameters. The decision criterion on the first stage and the decision criterion on the second stage. Only 2 free parameters. Moreover, the values for those decision criteria fall in plausible statistical range. That is, you don't have to assume some crazy value for these decision criteria, and adjusting them accounts for the differences between the subjects. Reasonably well.
Yes. So, when you said that if the p-value is not 0.5, then
Right.
you'll get an advantage by doing the recoding.
Yes.
Is it true that the farther from
Oh, for sure.
0.5 it is, the more the
Oh, sure.
advantage?
Just think about it for a while.
Yeah, no, I thought it was true.
You're going to have huge string. Suppose we get down to 0.01, right? You're going to have huge strings of zeros, right? So you can save a lot of memory by having a code for 22 zeros, right? It uses many fewer bits than 22 bits. Yeah. The savings become much greater the farther you get from 0.5. Yes, right.
The notion of try again
Uh-huh.
is fundamental to the ultimate answer as to what core learning mechanisms are about.
Yes.
Because the best example I can think of is, the kid's going along counting and says, no, try that again.
Yeah.
Right?
Yeah.
And there's a fair amount of that going
Yeah.
on.
Yeah.
Because how many trials they need is an open question.
Yeah.
But whatever their presupposition is
Yeah.
related to the hierarchical
Yeah,
structure
yeah.
with some probability, but it's quite skeletal.
Yeah.
And and you see this all the time in little kids.
Yeah.
Saying, no, let's try something else.
Yeah. Let's and see whether it fits with our
And
model.
I mean, I don't know how to begin to model it, but it
Yeah.
clearly would be
Yeah.
a learning model
Yeah.
about innate predispositions
Yeah.
that have built into them
Yeah.
structure
Yeah.
and probability, but not perfect.
Yeah.
Can't be, because we know that kids in different countries might use the same structure, even example of a structure, and then give it up.
Yeah.
But it's going to be true for a whole bunch of things.
Right.
You get this feedback,
Right.
They keep getting feedback,
Right.
and how much of it they need is a whole open question.
Right. And I would add that
Huh?
this is not really a follow-up to your
Sure.
comment, but I'm as sure as I can be that the same thing's going on in the heads of the rats and mice. We have another experiment in which it's we make changes in the Bernoulli probability of 2 kinds of trials that the animal can confront. And both the mice and the rats make step changes to these step changes in the not gradual changes. If you're in learning, it's all, the learning establishment I've heard people tell me that if it isn't gradual, it isn't learning. So
Right.
the idea that learning takes lots of trials and then you sort of sneak up on it is very deeply embedded in the field. So the idea that you have animals making these step adjustments, right, where they're not doing gradient descent, but they're helicoptering from one minimum to another minimum, is really hard for people to digest. But we see exactly that in both the rats and the mice. Jacob will love this. And they're sensitive to the asymmetry in the Kullback-Leibler divergence. So the Kullback-Leibler divergence is called the divergence rather than the distance because it's asymmetric. The divergence of 0.9 from 0.5 is smaller than the divergence from what did I say, from 0.5 to 0.9 is smaller than from 0.9 to 0.5. So when you're switching from 0.9 to 0.5, the mice should catch on quicker than when you're switching in the other direction, and in fact they do catch on quicker. So whatever's going on in their head is sensitive to the Kullback-Leibler divergence, which is, I think it shows that they've encoding the sequence. So here's
And
something.
it's the same question.
Yeah.
Asymmetry of information.
Yeah, but the question is, if I could get Peter Latham to focus on this, I'm pretty sure he could prove it. But the question is, can any algorithm that doesn't know the sequence be sensitive to if it only has the running summary statistic, can it show an asymmetry? I do not know the answer to that question. This is why I cultivate friends who are much better mathematicians than I am.
What do you mean by knowing?
I'm sorry?
What do you mean by knowing only the running summary? I mean, only knowing the last?
What Jacob said earlier, yeah, only knowing the average of only knowing 5 out of 7 and not knowing where the 2 exceptions were positioned in the sequence. So if all you're trying to do is estimate the p, 5 out of 7 is all you need to know. That's what's called a sufficient statistic. It says nothing else. If God has told you that they all came from the same...
You're doing tens of thousands, so you would seldom see 5 out of 7. You would see 10,005 or out of 10,007.
Well, yeah, but since you believe that there are changes, the previous 10,000 are all history. Their only use is for instructing you on how often things change, right? Anyway, just let me make sure people are clear about this notion of sufficient statistic, right? So, what it says is if the task is to estimate the p parameter of a Bernoulli process, knowing the number of successes and the number of failures, you know everything that's relevant to that estimate. Nothing else about that sequence can improve your estimate. But if you're looking for changes, that assertion depends on the assumption that God has told you you're drawing from the same distribution. If God hasn't told you if there's changes allowed, now it gets more interesting.
But you in fact did this, you in fact showed us your second experiment where you in fact changed the p every time.
Indeed, yes. Indeed, yeah.
Do you feel you misled your subjects?
No.
No.
We told them what changed.
So you don't think you...
Moreover, our subjects seem to get a pretty good idea of how it changed. The aperiodic ones are, like this, and the periodic ones are like that.
But there are yet other possibilities that you could experiment with.
Yeah, I know. I'm hoping the rest of the world will do that. There's quite a lot more that could be done.
So I can't resist asking one kind of much bigger picture question. So, so you had data before that showed that you mentioned that their estimates of the underlying p are equally accurate at both ends of the scale as they are near the middle, right? So
which is pretty surprising.
Yeah, well, so that's my question. How do you reconcile that with the bit of dogma that we hear from the judgment decision-making literature that small probabilities are overweighted and large probabilities?
So I came to Danny's talk with the intention of asking him that question, but the talk wasn't going into that territory, so I kept my mouth shut. But that's a great question, and part of the answer, but only part, is that an awful lot of that concerns relative likelihood rather than... Keep in mind, when people run the relative likelihood experiments, they almost always couch them as probability experiments. They say, what's the probability that it came from urn X, right? And I've never seen an experiment of that kind where they asked for the odds. It would be really interesting to see if you got different results if you asked the same subject for the odds. But there's very consistently, if you do that experiment, the subjects underestimate the probabilities, right? But what they're estimating are really probabilities, they're relative likelihoods.
Well, you said something earlier about what you meant when you said the accuracy was the same. But you don't mean, are you counting an error between 50% and 51% the same as a difference between 1% and 0%?
So that's why we ran two error messages, two error measures. If you just do least squares, yes, you're counting those differences, which, as you clearly perceive, is pretty crazy.
Well, I don't know if it's crazy, but maybe people mean different things when they're saying that the low probabilities are
But we didn't, but we ran the appropriate measure for just the Kullback-Leibler. I'm pretty confident that most professionals would say, yeah, the Kullback-Leibler is the right way to measure accuracy in this situation. And it does not have that problem.
But it's still making some choice about.
It tells you how, for any two pairs, how much information you are, for any two p-values, it tells you if you're going from this to here, you are getting this amount of information per draw. And that's an objective fact. That has nothing to do with psychology.
But is that,
Well, it's used in the servers all the time.
so is that what the judgment and decision-making people are saying? Are they contradicting?
No.
No, are they, what Jonathan referred to, what Jacob was talking about what the judgment and decision-making people think, is that inconsistent with there being the same on a Kullback-Leibler scale?
Yes.
I don't know, but, I mean, the classical example of these are things like subjects have, a very different percept of the difference between a 0% chance of a lottery ticket and a 1% versus a 90% and a 91%.
Well, maybe it's not inconsistent with what you say.
Well, no, wait a second.
I'm not sure.
No. So, the reason I'm chortling is because, in fact, if they pose that choice, which they often do, then the Kullback-Leibler says, oh, that's a very special choice. Because that is, it picks out the extreme values because the divergence goes to infinity. Those are singularities
Divided by 0.
and the divergence, and it's worth intuitively seeing why that's the case. So keep in mind, the Kullback-Leibler tells you how much data you'll have to get to achieve a given level of certainty about whether there's a discrepancy between what you think the truth is and what the truth actually is. Is everybody? Yeah? Okay. So you have to be clear. It's an observation. It applies, by the way, not just to the Bernoulli. It applies to any probability distribution. But and it's used in servers because they use it to recode the data when they run it. But to repeat, it tells you how much data you will need to get in order to reach some specified level of certainty about whether you're wrong, right? As a function of how far away the distribution you're actually drawing from is from the one you think you're drawing from, okay? Now, suppose you think all swans are black. But suppose 1 in 100 swans is in fact white. Okay. So first of all, what's the expected number of swans you'll have to observe in order to see your first white swan? It's 100, right? How certain will you be that you are wrong when you see the first white swan? You will have infinite certainty, right? Well, infinite certainty from one observation implies that the rate itself is infinite, right? And the Kullback-Leibler is the rate, right? Now turn it around. Suppose you think, no, I've only seen black swans, but I'm sure, I think 1 out of every 200 swans is white. So you've seen 1,000 swans, and they were all black. What's your level of certainty that I think you can intuitively see, wow, you're still very far from certain, right, that they're all black. I mean, you're going to be creeping up when you get out to 100,000, right? Well, you're beginning to wonder, but you're really going to creep up on that, on infinite certainty. Whereas going the other way, the first white swan, you have infinite certainty. So that just illustrates that these choices, if the brain actually knows this, then the extremes are game changers, right? They're singularities, right? And all bets are off when you get to a singularity. But to return to Barry's question, this is, no, hang on. So in prospect theory, there's a graph, there's this graph, and it says, well, what subjects think is the case is that, right? And we're not down here at 0.0. The Woodford, the economist, they went down to, I think, 1 in 1,000. And they said, yeah, there is some not in here. They would get down to 1 in 1,000. But they completely agree with me that between 0.01 and 0.99, it looks like this. In fact, their data look exactly like this. And Robinson's data looked exactly like this. These are the interquartiles, by the way. There's the median, and there's the interquartiles. So so this doesn't look anything like the curves that you see in prospect theory. And I can't stress too much that this is no surprise. This distinction that I began by making was made already by Peterson and Beach in 1964 in sort of the kind of a founding review in this whole judgment and decisions thing. And they made exactly this distinction. And they said already in 1964 that the relatively few experiments, but even then there were 20 maybe, that looked at descriptive probability, they all report that subjects are accurate, and they seem to be accurate over the whole range. Whereas when it gets to relative likelihood, which they called, and many people have, they called it reverse probability, right? Because you're reasoning backwards. And it's also been called inverse probability and so on. Yes.
So just, one more comment
Yeah.
on the Kullback-Leibler. So
Yeah.
another way of expressing in your context what it means is, so like before you were talking about how maybe the subjects are coding the past sequence, at least some amount of the past sequence, and if they are coding it as, if the past, n trials had probability P,
Yeah.
and they actually think they have probability Q,
Yeah.
in other words, they have the wrong model,
Yeah.
then the divergence, the KL divergence gives the extra amount of
Yeah.
bits that
Yeah.
it gives. And,
Yeah.
and so
It gives how many more registers in memory you're using than you
Right.
could use if you had a better model.
that's what I was driving at. So if you
Yeah.
think about it as literally as a memory model, as
Yeah.
opposed to just pure information,
Yeah.
it's literally how many neurons they're wasting
Yes,
by
yes.
trying to remember what happened.
I'm trying to get the neuroscientists to understand that
So
fact.
there's a huge adaptive pressure for them not to waste memory. So it makes sense for them to be very finely tuned at all ends of the scale.
Wouldn't it? Yes. Yes. Yes, but but the question you asked, I don't have an answer to that question you asked. And there are exceptions. So one well-known study that is clearly a descriptive probability asked people, it was Edwards, he asked, I'm a little worried I'm going to get it slightly wrong, but he asked people what the frequencies of various letters were in English.
Oh, that's Hatcher and Sachs.
They did some.
And
This
their
was
subject
Edwards,
said,
I
I
think.
can't do this. But they
Okay, but
could.
anyway, subjects were
Yeah.
not good at this. Whereas, as Heckler and Sachs showed in general,
They could do it.
subjects for most things have fairly accurate estimate
they
of
had to
frequencies
do was
over
say,
many orders
what
of
was the-
magnitude, by the way. Over 5 or 6 orders of
And
magnitude.
it had to do with, what's the most frequent letter, and so on.
Yeah.
And they said, I don't know.
Well, if you forced them, you got data that weren't crazy. They were sort of S-shaped and so on, but they were certainly didn't look like that.
I actually tried to get the
Yeah.
data, but Lynn threw it out.
I mean, of course, those are embedded in highly structured inputs, and I think that's part of the, I think subjects are having difficulty penetrating through the structure or something. That's a hand wave, but, yeah. And,
Well, you don't store everything in your memories. You
Well-
don't encode everything. Your experiments are telling the people this is what you encode, this is what you do.
So, I'm a heretic by nature. I like, and of course the working assumption in psychology in general is that of course you don't store everything. But if you kind of skeptical about that assumption and you start perking up whenever evidence comes along that you store one hell of a lot, there's actually a lot of evidence that you store a hell of a lot. The best known evidence is there's a whole line of experiments that began with Roger Shepard back in the 60s, I think, yeah, who sort of the most boring visit you ever made. You go to somebody and they've taken 10,000 slides of their most recent vacation and they're determined to show you all of them. Worse yet, then they're going to start showing you the rest of their slide collection afterwards and asking you which ones came from their vacation and which ones didn't. That was basically Shepard's experiment, right? I mean, how many did he show? I don't know. It was thousands. It was thousands. Okay, so he showed people thousands, literally, of just color slides. You know, just color slides picked out of his discard pile. And then he showed them pairs of colored slides and said, which one have you seen before? And subjects were way above chance, like 80% or something like that.
So are little kids.
Right, the little kids are, and so subjects were way above chance on this. Subsequently, I've got this reference someplace, but someone much more, there's several experiments following up on it. It's been replicated many times. A more recent one showed people line drawings. So line drawings of a piano, line drawings of an iron, line drawings of a chair, and so on. And again, thousands of them, okay? And now the probes was another line drawing of an iron, but in a different orientation, and the chair was in a different orientation. So people were way above chance at discriminating the line drawing of an iron they had seen from one that was the same drawing in a different orientation. So what does that tell us about how much they're remembering? I mean, and I think these experiments, our model requires that that people are remembering this sequence back hundreds of trials. And the reviewers just thought that was beyond scandalous, right? It couldn't possibly be true. But we got it published eventually. Anyway.
Are you thinking this is episodic memory, like, or an event memory, or as a form of semantic memory?
They're episodes.
So if you take out, if you were to remove hippocampus, or has anyone looked at this in people with episodic amnesia to see whether they track in a stepwise fashion?
Keep in mind, we're running, these mice are showing the same thing in this, basically. That is, our mice are almost ideal detectors of changes in the relative probability of short and long trials. And these trials are separated by minutes, right? So, in other words, it takes them the better part of an hour to accumulate 10 of these trials, right? And if you change the p-value, they change their behavior in step form at about the time a professional statistician would have told them that the p-value had changed, right? Now, how they're doing that if they're not keeping track of the sequence going back many trials and extending hours back, I don't know.
Who's doing that?
Huh?
Whose
So-
work is that?
That was Aaron, well, that started with Fulop's thesis, but it was Aaron's thesis
Sorry?
Aaron Heifetz's thesis.
Yes.
Looked at, among other things, the Kullback-Leibler asymmetry in mice's detection of changes in the yeah.
But if it's that long, then they remove the hippocampus, the rat's not going to be able to do that experiment.
Probably.